Morning, everybody. So I've given you all a card. I want you to write for just a minute before we get started in today's material. Imagine a scenario where, well, this is a real scenario, right? There's an upcoming exam, and you're going to have to study for it, right? But also imagine another scenario where I asked each and every one of you to teach the review for the exam. Which one of those would you spend more time on, and why? That's what I want you to write about. Yep. There is not a wrong answer. I'm curious.
So the question is, we spend more time studying for the exam
or preparing to give the review for the exam to the entire class. If I had assigned each of you, if I said, Elizabeth, you're going to give a review for the entire stuff for the exam, which one would you spend more time on? Studying for that upcoming exam, or preparing to teach people through the review for that exam? Yeah, put your name on it. That's fine. And again, there's no wrong answer. Just give me a good rationale for which one you choose. Give you a couple minutes. That's fine. So we're going through a quick little writing exercise where people have been asked, would you spend more time studying for the upcoming exam, or would you spend more time preparing to give a review if I asked you to give the review to the class for the exam? Which one would you spend more time on? Preparing to teach somebody, or just preparing yourself? Just keep it for now. About one more minute, and then we'll get started. All right, let's go ahead and get started on today's stuff. So last time we talked about the idea that we could form hydrates by the reaction of carbonyl compounds, ketones and aldehydes, with water. We could form these so-called gem diols, or these hydrates. And really, I said this is nothing more than just adding water across a carbon-oxygen double bond, right? That's really what we're doing. This is an equilibrium. It can go back and forth, okay? The equilibrium expression is written up here, okay? Products over reactants. The reactant, of course, being water, is pulled out of the equation. Can everybody remind me as to why it's pulled over to the other side? Because KEQ, right, is products, which would be, we'll call that B, We'll call that A. And water, of course, is a reactant. Why did we pull that over and say that K prime, as they call it, is equal to KEQ times the concentration of water B over A?
Because when you're dividing by something, multiply by it, so the same thing.
You're just talking about the mathematical operation. But why is it legitimate for me to pull water over on that side and call it K prime? Why is it legitimate for me to multiply this side and this side by water? Yeah, I can do it, but why is it legitimate? No. Means legitimate. Why is it? I mean, I can do all kinds of mathematical operations on something that make absolutely no sense, right? Why does it make sense that I can pull water out on this side, bring it over here, and combine it with KEQ and call it K prime? Why is that legitimate to do? There's nothing wrong, as Aubrey said, with my math. The math is correct, but why is it a legitimate operation to do? I can show you things where I can multiply both sides of the equation by something, and it's not a legitimate thing to do. I could give you situations where doing this isn't legitimate. Why is it legitimate? It is. It does have to do with the amount of water. What do you think the solvent is here? Are you sure? If I was wanting to set this up and I wanted the equilibrium to go all the way to the right, what would I use? I would use water. And why would I use water? Le Chatelier's principle would allow me to convert all of my ketone in this case, or aldehyde, whatever we're talking about, over to the gym dihydrate, or the gym diol, right? So, right, it makes sense that we would use water as the solvent. So now, with that information in mind, why is it perfectly okay for me to remove water from this side of the equation by multiplying both sides and calling it a new K prime constant? Does it go away? It's reused up. What's the concentration of water? We've talked about that before. Oh. Approximately. Is it a molar? If you had pure water, would it be 1 molar concentration? About 55.5 molar, right? More or less. Rough numbers, right? That's really concentrated, isn't it? So as it reacts, do you think my concentration of water is significantly changing? No. So it remains constant. So I can simply multiply both sides by water. Since it remains constant, it's not changing. I can do that, and now I only have to pay attention to A and B. Okay, that's why it's legitimate to do. Okay? If I were to use a different solvent and water was a limiting reactant, for example, I couldn't do that. That wouldn't be a legitimate mathematical operation anymore. Yeah, I'm not breaking any algebra rules, but on a physical sense, it would not be, because it would be a changing concentration. You can't do that, because that would mean that your constant would not be constant. It would be changing, right? But since the concentration of water, for all practical purposes, is remaining constant, we can pull it over to the constant side, and it's legitimate. Okay? So you can imagine that the equilibrium will lie to the right if K prime is large or small. The equilibrium here will lie to the right if K prime is large or small. Yeah, big. Yeah, so it's large, right? And it will lie to the left if it is small, right? If it's a small number, right? So, very good. So, just dealing with those types of things. So, if we look at this, what do you notice? So, here we've got several carbonyl-containing compounds. Here we've got formaldehyde. Here we've got acetaldehyde. Here we've got acetone, another aldehyde, another aldehyde, another aldehyde. What can you tell me? Okay, so ketones are clearly, do they lie to the left or to the right? They lie to the left. But aldehydes, right, like right here, lie to the right. How about these? To the left. It's a positive value, but it's still not, I wouldn't say it's lying exclusively to the right. But what about here? 2.8 times 10 to the fourth? It's lying to the right, correct? All right, very good. So we know that aldehydes form hydrates better than ketones, but what else can you tell me? What is this information also telling me? Electron withdrawing groups on aldehydes push the equilibrium to the right. What else? What about R groups? Push it to the left, right? What do you think it pushes it to the left? It is electron donating, that's right. Okay? It also has some steric effects, because if you look here, what's the difference between these two? Just the size of this group, right? For the most part. And so you can see that both steric and electronic factors come into play. Okay? So, ketones don't favor this formation. Aldehydes, for the most part, do. And then there's these other factors that we have to keep in mind. Okay? And that comes out of the mechanism. Now let's look at some real numbers. For those of you who are in biology and you go to your lab and you reach in and you pull out one of the frogs you're going to dissect, right? It is stuck in a solution that your biology teacher tells you is formaldehyde, right? It's a formaldehyde solution. It's actually formaldehyde in water. Do you really have formaldehyde? No, 99.9% of it is the hydrate. And they actually write on the bottle formalin, not formaldehyde. This is formalin. Okay? But it's in equilibrium with formaldehyde, and it is the formaldehyde that's the preservative. Okay? But it turns out that formaldehyde itself at room temperature is actually a gas, and it's kind of difficult to deal with. Okay? So what do? They bubble this gas through water. They make the formalin product that they sell to these biological supply houses. They pour it into a vat of frogs that are dead, and they preserve them, right? And so you always have a little bit of the formaldehyde around, which is responsible for the preservation of the tissues, okay? But in the bottle, most of it is the hydrate. Acetaldehyde. Where do you get acetaldehyde from? What would we oxidize to get acetaldehyde? What alcohol? Pardon? Ethanol. That's exactly right. This is what your liver does to beer. It oxidizes ethanol to acetaldehyde. What's in your blood? Water, right? So your liver oxidizes the ethanol to acetaldehyde, and in the blood, the acetaldehyde is in equilibrium with its hydrated product. About 58% of it is as the hydrate. The remaining is as the acetaldehyde. Okay? It's in equilibrium. Acetone, a ketone, right? So you've got some paint you want to remove from your hands. Maybe you've been painting, or you've got fingernail polish on that you want to remove. You go to Walmart, you buy some fingernail polish remover, acetone, right? It's water soluble, but very little of it actually forms the hydrate. Most of it exists as the ketone, which is kind of convenient because the ketone actually will dissolve the paint. The hydrate will not. Why? This is more polar than this, right? And most paints are non-polar. Okay, so like dissolves like, right? So this is convenient for us. Okay, so you have very little of the hydrate product in that case. Let's work through the mechanism. And let's just use formaldehyde. So we have formaldehyde, and Sarah bubbles it through water, and she gets the hydrate. Help me walk through the mechanism. How does that happen? Where do I start? Pardon? On the oxygen from the water. What do I have there? I've got lone pairs. So I've got a decent nucleophile. Water's not a great nucleophile, but it's 55 molar. So, yeah, it's going to work okay. Do I have an electrophile? I have the carbon of the carbonyl, right? And why is it an electrophile? Okay, so we've got a partial positive here, a partial negative here, and we've got a dipole in this direction, right? We also have a weak pi bond, right? And so push the arrows. And again, all of this is reversible. Now what happens? Pardon? How do I do that? Why is it that and not water? That's true, and what else? What's the pKa of water? Okay, close enough. 15.5, 15.7, right? In that ballpark. What's the pK of H3O+? It's a lot lower, right? Let's not worry about the exact number. What's that look like? So I've got a strong base, I've got a strong acid, it's got to react, right? And we're going to then get our hydrate. It's pretty simple, right? And it's perfectly reversible, okay? So if I want to form the hydrate, I use water as the solvent, and it will take my formaldehyde and convert it 99.9% to the gem diol. How do I go the other way? I could technically here add heat because formaldehyde's a gas and I could bubble it out. I'll give you that. That'll work. But chemically, how else could I do it? I could dehydrate it. That's exactly right. I can remove the water, right? So if I start removing water, it goes back and forms carbonyl. So this is a perfect way in which we can add something and take it off using essentially the same reaction. Okay, it's just a reversible process. Okay, very straightforward. Now, if we can do this with water, we should be able to do the same chemistry with alcohols. And why is that? They are kind of the same. Why are they kind of the same? pKa's are pretty close, that's true. What else? Lone pairs on the oxygen. What are alcohols? Alcohols are nothing more than organic derivatives of water, right? Because we can make an alcohol by adding water across a carbon-carbon double bond, for example, right? So we can actually do the same type of chemistry where we take a carbonyl alcohol and we get what's known as an acetal. Okay? We get an acetal. If I say that enough, I'll eventually mess it up. Okay? But that's what we get. How does an acetal look like a hydrate, and how is it different? Okay, very good. Right, so we've got two oxygen atoms bound to the same carbon atom, so it kind of looks like a gem diol. You might call this a gem diether if you want, right? Because this kind of looks like an ether, and this kind of looks like an ether, right? They just happen to share the same carbon. Okay. How are they different? They're ethers instead of alcohols, right? So would we expect them to have the same chemistry? Or the reactivity? No. They're actually quite different. If I make a diol, I still have OHs, which are acidic, and they can mess with other chemistry that I want to do. Here, however, ethers are pretty inert, remember? Right? And we can actually use this chemistry to protect a carbonyl compound if we want to leave it alone. So for example, imagine you wanted to reduce an ester to an alcohol with lithium aluminum hydride. But in the same molecule, you also had an aldehyde that you wanted to leave alone. You can't just throw in lithium aluminum hydride and do that, right? Because it will react with both species. And in fact, it will react with the aldehyde first, right? So you're kind of up a creek without a paddle. But we know that aldehydes are more reactive to forming acetals than are esters. Esters don't do this. And so we could actually protect the aldehyde as an acetal. There's no hydrogens there for the lithium aluminum hydride to react with. We could then go and do the chemistry with the lithium aluminum hydride, and then at the end we could just reverse this reaction and get our aldehyde back. This is another way to do protecting groups. Okay, we've talked about protecting groups in the past. We've protected alcohols. How did we protect alcohols? We made them into ethers, right? Either a trityl ether, a tert-butyl ether, or a silyl ether, right? We talked about those chemistries. Now we have a way in which we can protect carbonyl-containing groups, which is kind of convenient for us. Now, this chemistry occurs best if you have an acid catalyst around. And the acid that we like to use is either a trace of sulfuric acid or paratoluene sulfonic acid. And in fact, throughout the book, they'll probably use paratoluene sulfonic acid more so than sulfuric acid, okay? And so you take the aldehyde, the methanol, the paratoluene sulfonic acid, there's just a trace of it, and you can form these two new sigma bonds, and the equilibrium is going to be shifted to the right. Okay? But it's an equilibrium, so there's always going to be some of this around. That's going to make for a really sucky protecting group strategy if I get a 50-50 mix, right? How do I push this all the way over to here? I could add more methanol. That's one way. What's another way? Take away the water. Which way do you think most people like to do? Take away the water, right? And quite frequently we will distill the water out. Kind of hard to do with the methanol because methanol boils at a lower temperature. But for other alcohols that are higher boiling, usually what we do is we just boil out the water, okay? And so we can push the equilibrium to the right, okay? So here's the example. We've got a ketone, we've got an ester, okay? We want to do some chemistry on the ester. Let's say we want to reduce it to the primary alcohol. Not going to happen because we know that ketones are more reactive than esters. But what we can do is we can protect the ketone, leave the ester alone, do the chemistry, and then get back to where we want to be, okay? So for example, here's how we would do this. We have our ketone and our ester in our molecule. What is this molecule? It is a diol. Anybody remember which one it is? It's got 2 carbons, so what do we call it? Close. What's the commercial name? This is what's in the old antifreeze, not the new antifreeze. Propylene glycol is the new antifreeze. Ethylene glycol, that's right. This is the old antifreeze, right? This stuff, by the way, is extraordinarily sweet. Okay? Don't drink it, though. It's also extremely toxic. Why would we use this? What's convenient about it? It is cheap. What else? It's one molecule, and it has both alcohols in the one molecule, right? So we just need to use a single equivalent of this, or if we have a mole of this, we just need a mole of this. We'll use some inert solvent, methylene chloride or whatever, paratoluene sulfonic acid, and we can protect the ketone. It leaves the ester alone, okay? Because this only goes after aldehydes and ketones. So we've made this cyclic acetal. We no longer have a weak pi bond. So when we do the reduction, can lithium aluminum hydride reduce esters? No, it leaves it alone, or excuse me, ethers. No, it leaves it alone. So we do the reduction of the ester, and we know that esters plus lithium aluminum hydride followed by quenching give us a primary alcohol. That's what we get. And so now we've got the alcohol that we want, but now we want our ketone back. So all we have to do, right, is just dump it into a large amount of water and reverse the reaction. And so when we do that, we get our ketone back plus our diol, and we just separate these two by distillation or something like that, and we can get our ketone now. If we had tried to do this where we were just doing the reduction, it would reduce the ketone first. and eventually also reduce the ester if we had enough lithium aluminum hydride around. So this is how we have to do this. So this is a protecting group strategy. Okay? Now, I want us to work through the mechanism together. So let's take this ketone and let's take ethylene glycol and a little acid. So let's just, for brevity's sake, call it H plus A minus, just to make life easy. And we're going to make our acetal. How do we work the mechanism here? It does, but does it do it first? I need a catalyst, right? I said we're going to add a catalytic amount of this acid. We are going to have to protonate something first. What are we going to protonate? We've got two of them. Technically, it will protonate the alcohol, but it'll also protonate what else? The ketone. It'll protonate the oxygen of the ketone. Sarah's absolutely right. All the things that have lone pairs are going to get protonated to some degree. Okay? But protonating the oxygen in my mechanism on the alcohol doesn't help me, right? Because that's a dead end. That no longer is that oxygen nucleophilic. What I need to do is I need to make the carbonyl more electrophilic, right? We need to make it more reactive. That's what the catalyst is going to do, right? If you think about it. So what's going to happen in the first step, I'm going to protonate the carbonyl, oxygen, and I have to draw this as equilibria. Does equilibrium lie to the down or up? What do you think? Okay, you're on the right track of thinking about it. So we need to look at pKa's, right? Now, paratoluene sulfonic acid, a strong acid or a weak acid? Strong, meaning it completely dissociates, right? What about something that looks like H3O+, strong acid or weak acid? Strong. So I'm going from a strong acid to a strong acid. Which way is the equilibrium going to lie? Well, that kind of looks like H3O+. There's not, but there's an oxygen with a positive charge and a hydrogen, right? So would I expect this to be happy protonated all the time? No. Actually, the equilibrium lies up here, okay? But you get a significant amount of this, and once you get this, it's more reactive than the starting material, so it's what does the chemistry, right? And so now I have a ketone, a carbonyl functional group. Is it more reactive now or less reactive? More reactive. Why? Why is that going to be more reactive towards nucleophiles? All right. What's happening if I just look at the, let's look up here. If I'm looking at the carbonyl, you told me earlier that it's polar, right? You have a partial positive charge here and a partial negative charge here. If I put a positive up here, what happens to the positive down here? Less? More. Why does it get more? Because it wants more electrons. Oxygen doesn't like to be positively charged. Where can it get them from? It can get them from that carbon-oxygen pi bond. That's the easiest place to get them. That's the weakest bond. So that makes this carbon very more positive, makes it very electrophilic, right? And so now, and it doesn't matter because it's symmetrical, right? Now it gets a little more complicated. You do know what the product looks like. Something comes together. What did we not put up there at the top? What's the other product? Water. Let's be fair and balanced here, right? As they say on the TV. What happens? Which alcohol? I've got two of them up there right now. On the left, on the right. So if this alcohol gets protonated and it leaves, what kind of carbocation would that give me? Primary. Is that going to happen? No. But I have this one, right? I've got this one. So it could get protonated, right? How does that happen? Have a little bit of it. We actually do what's known as a proton transfer. Turns out it could come from a variety of sources, but and of course I've got my A- around. Let's just keep everything fair and balanced here. Now what happens? The H2O can leave at this point, right? Right, so we can lose water. We got to get water somewhere, right? Looks like we got water. Just has to leave. How does that happen? Does it just leave and give me a carbocation? Help me out. Let's struggle through this together. We've just determined it probably isn't just going to leave on its own, right? Something's going to have to help push it out. What can help push it out? Pardon? Which oxygen? The ether one? The other one? Okay. Not a bad thought. But think about it in terms of kinetics. Which one's going to be faster? The one closest, right? And so it actually turns out, yeah, you could get directly to the ring that way, but experimentally we've determined that that's not the case. The electrons are right here. These are out there flopping around, right? But these are right here, right? This comes back, kicks out water. We now have double bond O. It's got a positive charge. Now what happens? What do you think happens now, John Michael? What about this? That's starting to look kind of like where we started, right? What happened then? What happened here? The OH attacked. Is that any different? Not really. The OH is actually now attached to the molecule. So how do I push the arrows? Okay. Getting close. Man, we formed the ring. Now what do we have to do? We have to deprotonate. And I can deprotonate now with the A- and get back my catalyst, right? Or the water can deprotonate it, depending on how much water you have around. Doesn't matter. It's the same thing. It's a strong acid. And then that gets me to the product. Again, a lot of steps, but they're all elementary. Everything up there is an acid-base reaction. And you're going to tell me what they are. What's the acid, what's the base in this very first step? H plus is the acid, and the oxygen of the ketone is the base. Lewis acid, Lewis base. What's the Lewis acid and what's the Lewis base in the second step? Okay, the base is the oxygen of the alcohol. The protonated carbonyl is now the acid. It's the electron pair acceptor. What's the acid and what's the base here?
Base is the
Okay, and that's the acid, right? And we get a proton transfer. What's the acid and what's the base here? Is what?
Is the base.
Base, acid. What's the acid, what's the base here? Base, acid, right? What's the acid, what's the base? Obviously the base, the acid, and you get the product. It's nothing more than a series of acids and bases, which you all learned in general chemistry, and Le Chatelier's principle, which you learned in general chemistry, both of which I told you would haunt you for the rest of your life, right? But it's a lot of steps, and they're all equilibria, okay? So John Michael wants to take this ketone and completely convert it to this acetal. Ethylene glycol's cheap, but it's not free. So, you know, being the thrifty person he is, he doesn't want to use too much of it. Plus, it's also got a high boiling point. It's hard to get rid of, right? So he uses one equivalent. So how does he drive the equilibrium to the right? He removes the water by distilling it out. Nice and convenient. Now he made this for his customer, and his customer does some chemistry and then wants to get the ketone back. How do they get the ketone back? How do they make it go backwards? You add a bunch of water and a little bit of acid catalyst, and it'll just go the other way. Okay? Le Chatelier's principle, acid-base principles, the biggest things that you need to keep in mind. Open up. What did I do with them? It's from another set of slides. It's the same chapter. Same chapter. Just from a different book we used to use. Today we're going to continue talking about things that we can add to carbonyl compounds. At this point, what have we talked about that we can add? Obviously, we can add water and we can add alcohols. We can get diol or gem diols and we can get acetals. Okay? We can also get what other things to add to carbonyl compounds? Grignards. What else? Pardon? Mm-hmm. What else? And hydride, right? We can add H minus. Well, there's other things that we can add as well. We can also add other types of carbon. And we can add amines. Okay? We've already talked about water and alcohol, so I'm going to skip that part today. But the Wittig reaction is a classical reaction that's used on a laboratory scale a lot of the time. However, it's not very useful industrially because the waste that you generate, triphenylphosphine oxide, is a lot of mass. And how does the waste company handle your waste? Per pound or per unit volume. But it's based on that type of quantity. They don't do it on per mole. Okay? So I take a cheap aldehyde. I take a cheap what's called a Wittig reagent. We'll learn more about that later. I make a new alkene that's probably cheap. And now I got to dispose of this stuff, which can be kind of expensive. Okay? How do you all know how to make alkenes at this point? Elimination of what? Water. So we can take an alcohol and we can dehydrate it to an alkene. We can remove halogen, HX, right? We can get an alkene. Now, notice what we can do. We can take an aldehyde or a ketone, and we can turn that into we can convert that from a carbon-oxygen double bond to a carbon-carbon double bond using what's known as a Wittig reagent. What's strange about this Wittig reagent? It's got a what? It's got a W instead of a V? It's because it's German. Carbon has a lone pair of electrons and a what charge? Okay, and phosphorus is positively charged. When we have a molecule that has both a positive and a negative charge, what did you learn those were called in Gen Chem? Okay, they're kind of like a salt, but it's a salt that's connected together. What did you call those? Zwitterions. You remember the Zwitterion? No? You should have learned it, okay? Zwitterions are molecules that have both a positive and a negative charge within them, okay? And they are kind of like connected salts. You can think of them that way. There's nothing wrong with that, okay? And it turns out that these Wittig reagents are Zwitterions, and so this carbon is actually a pretty darn good nucleophile, and it will attack the carbon of the carbonyl and ultimately spit out triphenylphosphine oxide, which we'll talk about, and give us a carbon-carbon double bond. The cool thing about this is this reaction is so easy to do. That's why we love giving it to you all. Okay, it's one of the reactions you all are going to do. And one of the reasons why I love it in my lab is because I can give it to anybody, and if they come to me and say, oh, it failed, I'm like, no, you lost it or something, because this reaction doesn't fail. Okay? These things are so easy to do. I did a lot of these when I was a postdoc. You literally take the aldehyde, the Wittig reagent, you mix them up in something like hexane or methylene chloride, you stir them, you come back the next day, the triphenylphosphine oxide is not particularly soluble in hexane, you filter it off and you're done. It's great, right? It's great chemistry, okay? So for example, and this works equally well with aldehydes and ketones, so we can take an aldehyde, we can take this ylide and we can make an alkene quite easily. We can take this ketone, we can take this ylide. Notice there's other carbons here, but they don't do anything. They're just along for the ride. We can make this alkene. So we can make all kinds of different alkenes from Wittig chemistry very, very easily. Okay? You will see Wittig reagents drawn in a couple of ways. You can see them where all the aromatic rings are actually shown, or they'll just abbreviate an aromatic ring as a phenyl ring as a pH. These are equivalent. These are the same thing, okay? So you need to know that. This is known as an ylide, okay? An ylide is a molecule that has two of the same charges, but they are perfectly adjacent to one another like this, okay? On adjacent atoms. It is a Zwitterion, but they are right next to one another, okay? And these are what we call phosphorus ylides. We quite frequently abbreviate them even further like this. PH3P double bond C. And I can do that. Why can I do that without breaking rules? I got 10 electrons around phosphorus. Is that good? It's not bad. Why? Phosphorus isn't in what period? Remember, the octet rule only applies for the second period, right? So we can have 10 electrons around phosphorus, actually. And quite frequently, we draw them like this simply because it's easier to do in my software. I don't have to click on plus, I don't have to click on minus, I just draw a double bond between the phosphorus and the carbon. But you need to know, when looking at this, that the carbon actually is the negatively charged species and phosphorus is the positively charged species, okay? These Wittig reagents are extraordinarily easy to make. Oh my gosh, so easy to make. So you take triphenylphosphine and you take a primary alkyl halide and you get what's known as a phosphonium salt, which some of us call Wittig salts. It's not really the right term, but it's what we quite frequently refer to them as because we're going to use them to make Wittig reagents. This is an SN2 reaction, right? Triphenylphosphine actually turns out to be a pretty good nucleophile. Remember, what happens to nucleophilicity as we go down a family? It increases. So we would expect phosphorus to be a better nucleophile than nitrogen. Guess what it is? We're using a primary alkyl halide. What can X be here? Chlorine, bromine, or iodine. It cannot be fluorine. Fluorine's not a good leaving group. This is an SN2 reaction, so the rate of the reaction is dependent on the concentration of both species. This is soluble in hexane. This is soluble in hexane. What do you think about a salt? It is not. Again, a very easy reaction to do. You take 1 mole of the triphenylphosphine, you dissolve it in hexane, about 1 liter. You take a mole of your alkyl halide, and if you're rich enough and in a hurry, you buy the primary iodide. You throw it in there, you put a stir bar, and you let it stir for about an hour, and all of a sudden you come back and there's this white, fluffy solid in the bottom. You filter it, and you've got the phosphonium salt. Is that a Wittig reagent? What does it need to be a Wittig reagent? Negative charge on the adjacent carbon. What do I have to do to get a negative charge there? Well, okay, I have to get some electrons there, but how do I do that? I need to remove a hydrogen. How do we remove hydrogens from things? With a base. That's right. So I need a base that will remove one of these hydrogens. What base do you think we might use? Strong base? Weak base? It's going to be a fairly strong base, but it doesn't have to be the strongest bases, because these hydrogens are more acidic than you might expect. Why? That's right. The positive charge on the phosphorus makes these hydrogens a little more acidic than you might expect. Okay? So give me some bases that you might just try to use. Pyridine in this particular case that we have here wouldn't work, but you can use pyridine if the R group is also electron withdrawing. It might work. Not strong enough for the most part. Typically, people use things like sodium amide, NaNH2 minus. That's a good one. People will also use butyl lithium as a base. Now, that's the strongest base you can pretty much so use, but they use it out of convenience, and it works. Okay? And so, yeah, the chemistry is pretty straightforward here. It's just acid-base chemistry again. Base abstracts the acidic hydrogen, and you end up with the ylide. Okay? And in this case, they're showing this as being butyl lithium. Okay? We're going to continue on this on Wednesday because we haven't gotten far enough. So the inverted lecture for Wednesday will be kind of some group activities as we finish up the chapter. Okay? So come prepared for that kind of stuff. And I'll see you on Wednesday. On your way out, just put your note card up at the front. Sir. Pardon? Butyl lithium is pretty much so the strongest base, yeah. Oh, wait, I've got some, well, I'll hand these back out on Wednesday. Everybody got a check mark, so good to go.